So guys, I was mentioning to Kang before class that I have a meeting with one of the authors of the planar vector fields paper, and so I'm going to talk to him about maybe, our possible project and some things. And I think in the process of that conversation, I'll get a deeper understanding of the paper. So I'm going to wait to talk to you guys more about that because, I could continue calculating through it mechanically, but I don't think it would really be interesting for you guys right now. I think it's going to be more interesting if I come back to it after I understand it a little bit better. So I'm shifting gears, and we're turning our attention to the problem of solving differential equations, systems of differential equations over an algebra, all right? And so let me just state the problem.
We're not in the paper anymore.
Well, this textbook is just, I'm just stealing a couple theorems from it. I actually have kind of a project for us today. I don't know if we have enough time for it or not, but we're going to try. All right? So the problem is this, generically speaking, is we've got something like, dw1 dz equal to, a11 w1 plus plus a1 and wn dwn dz an1 w1 ann wn. So in other words, I'm looking at the differential equation dw dz equal to aw, where w is something like a path in the algebra. Well, it's a path in, let's see here, the output is not in the algebra. The output is in an, I suppose, my current lingo, right? So a solution is a map like that when I differentiate the map w with respect to the algebra variable z, I get the same thing as just multiplying a by w. So, theorem, if there exists lambda in A and u in an non-zero, then, such that au equals to lambda u, then w equals to e to the lambda zu solve star. All right. The proof of this is not complicated, nor is it different than the one you saw in differential equations if you took it. You guys took it. So, just differentiate with respect to z, e to the lambda zu, and by the rules of calculus that I have almost explained in here, that's this, and the u is constant, so it just rides along. But then, of course, we can pull the e to the z, e lambda z out. We got ourselves a lambda u, which of course is au, which is a e to the lambda zu, which is aw. Okay, great. So, and this if I also tell you an initial data initial data, if I say w of z naught, is equal to w naught for a given a given initial data point, then this is an initial value problem. It's n differential equations over the algebra, and given an initial value, there exists a unique solution. I'm assuming that the a1, a11, a12, all the way out through ann, that these are constants for the sake of our discussion. And that's the focus of the problem right here. That's our starting point. And so that would fall under the purview of the existence and uniqueness theorem that I proved. In fact, you can prove that this will fit the bill. There exists a unique solution to this system. So the question that I'm confronting today is not whether or not a solution exists. I know a solution exists. The question is, what is it and how do we find it? Now, I already know this theorem still works. So if I can find eigenvectors, that gives me solutions. So what I want to describe to you today is the embarrassment of too many eigenvectors and too many eigenvalues, the trouble that we confront by looking at matrices over a ring. And so I'm going to present to you just a few definitions and results without proof from this book, Matrices over Commutative Rings by Brown. And so, let's see here. Just got to rattle off some definitions as fast as I can. So if we have A in an element of the n by n, this is notation, is this n by n matrices over the, well, I'll use the ring R. R will later, for us, be replaced with A, but for the sake of not butchering his results, I'm going to use R and just copy directly as to not confuse myself. And so here's his definition. This is on page 214 of this book. An element D in R is eigenvalue of A if A V is equal to dV for some non-zero V in Rn. So already you see that that's exactly my definition. I mean, I just, over here, my U is an eigenvector with eigenvalue lambda. Nothing surprising here, right? I use this term in passing, but the spectrum, and I don't know how to make his symbol very good, but so I'm going to use my S. S for spectrum. Spectrum of A. Spectrum of A. You know what? Spec. Spec of A, spectrum, is D in the ring such that what? Which of the spectrum? The spectrum is the set of eigenvalues. So it's D in the ring such that D is an eigenvalue of A. All right. C, you know, V not equal to 0 such that AV equals to DV is an eigenvector, right? It's an eigenvector of A. Right. And then D, the eigenspace, which I'll use this symbol for, eigenspace of D, what's that? That is equal to all V, right, in Rn, such that AV is equal to dV. So that's the eigenspace associated to D. Sometimes eigenvalues are called characteristic values. Sometimes eigenvectors are called characteristic vectors. All right? Of course, the eigenspace also includes the zero vector, which is not an eigenvector. Okay. Oh, are you laughing because you're remembering linear and my many vain attempts to get people not to give zero as an eigenvector? It's a battle I'm still fighting. I'll fight it again this semester, but I'm going to lose that battle. I will never win that battle. Well, I had a class repeat after me. I made them repeat after me. I will not put zero is an eigenvector on the test. Like, I made them repeat it out loud in words back to me. Still. King, you're not helping. All right, here. So the following sets are the same. Lemma 7.2. Oh, really?
No, I mean, they excluded zero in eigenvector, and then they didn't include zero in eigenspace. Like, this is like a roundabout wording.
Yeah.
All eigenspace is still all eigenvector. And then it's like,
So spec A is one thing you could say, but that's also equal to D in the ring such that the null space, which I usually use null for, null of D times the identity matrix minus A is not equal to 0, which is also equivalently D in the ring such that the characteristic CA of D is an element of the 0 divisors of the ring. Now that's not his notation. He has null equal to null space, and he uses, he doesn't say 0 divisors, he uses just a big Z for 0 divisors. Not to be confused with the center, which is why I don't use it. So me, ZD, 0 divisor. All right, great. Now CAD is what? That is the characteristic polynomial of D. Of A, rather. So that would be like CA of X would be the determinant of XIN minus A, I believe. All right, so another result we have, 17.3. 17.3, if we have D is in the spectrum of A, or there was D is an eigenvalue, and if we also have that AV is equal to DV for some V not equal to 0, then if the set, oh, check this out, King. If the set containing V is linearly independent over R, all right, then CA of D is equal to 0. So I'm suggesting to you guys that you can have a non-zero vector whose singleton set is not a linearly independent set. This is not something we have to deal with in linear algebra proper, right? You give me a non-zero vector and put it in a set, it's linearly independent. I mean, that's it, right? But not here. So what's an example of this not happening is something like what? Well, if we have a vector, yeah, you just need 0 divisors, basically. Something like, 1 plus j in H2. Hyperbolic, like hyperbolic 2 tuples. Then if we look at 1 minus j times v, we get 0. So that's a non-trivial linear combination of v, which is 0. So the set just containing v is not linearly independent. Well, this vector v, this linear combination right here is damning. This implies that this set just containing that v is not linearly independent, right? What was our definition of linear independence over a ring? It goes back to that, right? Definition, if we have a set S, v1 vn is linearly independent if and only if c1 v1 plus plus cn vn equal to 0 implies c1 0 and all the way on cn is equal to 0. To be clear, S is a subset of Rn, if you will. But more generally, it's a subset of an R module. And the coefficients C1 through Cn are coefficients they're taken from the ring, that's the base ring for the module. And we have to have that forces all the coefficients to be 0. That's what linear independence means. So that's not linearly independent. So, so the answer to Jess's question, if we're over Rn, it's coming from the zero divisors of Rn. But if we were in a more interesting module with torsion, it could be coming from the torsion piece. But even the concept of a torsion piece isn't given to us here because we're not working over a principal ideal domain. So the fundamental decomposition of PIDs is not available to us. We can't decompose an A module. We can't decompose an A module into a torsion piece and a free piece because it's not a principal ideal domain. So the yes. All right, I must get on with it. So here it is. The theorem that I'd like to explore with you guys. I mean, I'll show you the example he has, 17.7. And so the ultimate question for me is whether or not the matrix is diagonalizable, essentially. I mean, suppose it's got enough eigenvalues that it's diagonalizable one way. Is it diagonalizable just one way or more than one way? Is kind of the question. I mean, the answer to that question, which you might not even think to ask, is a little bit surprising. And here it is. So A in M n by n over the ring in question here is similar to diagonal matrix all right, if and only if, here we go, the union over D element of, what is that? Yar. What's that? R of A there? Oh, stink. Well, I'm going to write that, and then we'll try to figure out. We'll have to read back, but script R of A. That is a subset of the spectrum. What subset of the spectrum that is, I'm not sure yet. But anyway, this is some kind of subset of the spectrum. E of D. The union of those contains a free module basis, a free R module, to be more specific. R module basis of Rn. All right, so what's this mysterious RA? I just skipped a page. It's my own stupid fault, you know? All right, what's that RA? Those are the eigenvalues which actually make the characteristic polynomial vanish. So here, RA is D in the ring such that CA of D is straight up equal to 0. You notice that there are other eigenvalues, right, which are not as healthy, if you could say. I don't know. This may be for like you could say this is the regular part of the spectrum. It's the, Well, is that true? Well, that's not true either. I mean, it doesn't have to do with, this does not have to do with whether or not D is a zero divisor. It has to do with when you evaluate the characteristic polynomial of A at D, what happens. If when you evaluate the characteristic polynomial at D, you get a zero divisor, well, then it's in the spectrum, but it's not in this R of A, which has a name. Oh, this is the roots. This is the roots of CA of X, okay? I guess hypothetically, if we had CA of X work out to something like, 1 plus j times x minus 1 times x minus j, right? If that was the characteristic polynomial, then the spectrum of A would include 1 minus j. Maybe. No, the spectrum would include, what would the spectrum include? I don't know. I feel like that, something like this is how that would happen, right? Well, I mean, certainly, one and j, there's your roots, but then there's other stuff. Like, what can I plug in for x such that that works out to what? A zero divisor. Pretty much any x, yeah. As long as pretty much x not equal to 1, right? I mean, if x is 1, this is 0, so it's, I mean, if x is 1, it's here. Oh. Whoa. Like, this one's too bad, right? I think anything for, I mean, this is, I mean, I'm starting to think that this is H. Working over the hyperbolics. So King is trying to talk me down. He's trying to tell me I should do something like CB of X is something like, maybe it's something like this instead. So then the spectrum would include, of course, 1 and j. And how can I make that work out to a zero divisor? Minus 1? Very good. Minus j, yeah. What about like 2 plus j? See, because 2 plus j makes this into 1 plus j. I mean, but this is the roots of B, rather. Whoa, I start to appreciate how grateful I am that the theorem concerns the roots and not the eigenvalues. Yeah. Okay. How many roots are there for a quadratic polynomial over the hyperbolics? At most 4, right? Or none, right? So that's the theorem, right? So if you can look at the eigenspaces and pick a free module basis for Rn, that means that your matrix is diagonalizable. That's not too bad. I mean, in the usual theory, right, if we can find n, for example, if we could find n distinct eigenvalues, that would give us n linearly independent eigenvectors, consequently an eigenbasis, consequently it would be similar to a diagonal matrix with the eigenvalues down the diagonal, right? But you can see already that we're headed for trouble, because in the 2 by 2 case, right, if we have a 2 by 2 matrix with a hyperbolics, we have up to 4 roots, right? So how does that diagonalize? Like, which of the 4 do you take? Yeah, I don't know. Let's see how that works out. So this is the thing that I'm interested in, guys, is understanding this, weird behavior. I need some more examples of it. The example he has in here, well, it's lovely, but it's not where I do calculus, so it's not really interesting to me. I need to find a better example. So here's z mod 6z, but I think you guys can help me with that. Z mod 6z, which will use the notation 0, 1, 2, 3, 4, 5. Don't tell Dr. Sperano. Just kidding. I mean, this notation is fine as long as you understand that 0 is the equivalence class containing 0 mod 6. I don't know, but he is right that sometimes students who use this notation don't really understand it. Maybe this is a conversation I had with Dr. Smith. I can't remember. Anyway, so here's the matrix. Here's the matrix of the hour. 2, 3, 4, 3. Great. This is a 2 by 2 matrix, obviously. What's the characteristic polynomial of A? So we get x minus 2 times x minus 3 minus 12. So that's x squared minus 5x minus 6, I think. That's funny. And then what he has written is not that. Here's his characteristic polynomial. And you guys tell me why it's very reasonable. Yeah, 6 is 0. So, yeah. And so then okay, so that's, of course, we prefer this notation because it's less writing. And then how do you find out the zeros of a polynomial over Z6? You just plug them in, right? So plug them in. What's CA of 0? What's CA of 1? CA of 2? CA of 3? CA of 4? CA of 5? So we got 0, 2, 0, 0, yeah. 2? And 2, yeah. And then 25 plus 5 is 30, which is 0, yeah. Okay, so what's the spectrum of A here? Well, my question for you is 2 is an element of what? Much like I was just convincing myself in our more exciting example over there, the spectrum is everything. I start to think finding matrices in this kind of context which don't have a spectrum of everything is actually kind of special. I mean, I have the feeling like I'm being punked here, you know, like mathematical Ashton Kutcher's around the corner, ready to do something to me. Or something. I think that's too old and vague a reference. Anyway, are you guys? Yeah, okay. That's the spectrum. What's the roots? You got yourself a 0, a 2, a 3, and a 5. So then,
why do you care about the spectrum so much? Particularly in something later.
because well, I mean, I guess I care about the spectrum because maybe I don't as much. I mean, say this. I mean, all right. So this null space, right? The null space of d in minus a not equal to 0, right? Great. What does that really mean? Well, here's the finer print. The determinant of din minus a. If this is not an element, excuse me, if this is, how can I say this? I think if this is equal to 0, I want to say if that's equal to 0, that means that the null space actually has a basis which could be used as part of a free R module basis. However, if the determinant of that matrix is an element of the 0 divisors of the algebra we're looking at, it's still the case that the null space is non-zero. It's still the case that there exists a non-trivial eigenvector with eigenvalue d. However, the eigenvector supporting that is garbage, in the sense of it's not something I can complete to a free R module basis because it is got sort of stuff attached to it. It's something like this. I think that's how it goes. I could be wrong. I believe that's basically the story here. I mean, either this is 0 or yeah, if this is non-zero, that means the determinant has to be a 0 divisor. That's a theorem earlier in this book. Let me read the theorem for you. If I can find it. So this book has things like, it works out the theory of determinants over a ring, matrices over a ring, you know, basically how to solve equations in this context, like, you know, how row reduction and all that stuff changes and or is the same, you know, all of the things you'd like to know about are in here. It is that stuff. It's just much more concrete because we're talking about matrices over a ring as opposed to an arbitrary R module, which is, I mean, matrices over a ring is an R module, and how that works out is an example of that principle if the ring is a principal ideal domain. the same. If it's not, well, this is still true. So yeah, you're right. It's not the same, but it's could be related depending on whether or not R is a principal ideal domain. Yes. Sorry. Eventually, I'll find the theorem I'm looking for in here. Kramer's rule. Come on. I'm pretty sure it's back in chapter 5 of this book where he basically looks at what is the rules for solving systems of equations. All right. Come on. What's exciting is I'm going to go on. I believe that to be a description of what are the different cases. I know this much is true. This much I remember for sure. If the determinant of a matrix is a zero divisor, right? There exists infinitely many solutions in this context. Assuming we're working over something of characteristic 0. I mean, I guess if we're working in Z6, then still, yeah. But but the nature of that infinity of solutions is very different if the determinant's 0 versus if the determinant's a zero divisor, I think. So I'm not absolutely sure about what I'm saying here, though. I really should find a reference for it. That's what I think, but I could be wrong. Okay, so okay, so getting back to our example. So we need to look at what are the eigenspaces? What are the eigenspaces for our roots? Can we find those? What do they look like? That's just a straightforward linear algebra calculation, right? So you guys tell me, what does the eigenspace for 0 look like? So we're looking for V such that what? V in Z62 such that what? Such that 2, 3, 4, 3 times, xy equals to 0, right? Can you guys tell me solutions? Three, 2, yeah. I guess that should be it, right? Yeah. All right. This kind of calculation I'm not really that interested in. Let me just write the answers down for you guys. Because I really what I want us to do next is to try to find a similar example of the hyperbolics. All right? That is my goal for today. Come on. Lost my place. Come on, where'd you go? All right, so the eigenspace of 0 is, so we can write this as R32. That's a notation for span over the ring of R32. It's kind of cute. What's the eigenspace of 2? It's the null space of 0, 3, 2, 5, which, by the way, is R times 1, 2. The eigenspace of the other root 3 is the null space of 1, 3, 2, 0, which, by the way, is the span of the 3, 1 vector. Is that right? Oh, yeah. 3 plus 3 is 6, isn't it? Duh. Yeah. And then the eigenspace of 5 is the null space of, let's see here, I minus a, which in this case is 3, 3, 2, 2. And that is the span of 1, 5. So thinking about the theorem I wrote down, the union, right, over D in the range, the roots of A, right? It contains within it what? You got yourself what, like 3, 2, 1, 2, 3, 1, 1, 5. Does that contain a free module basis for 2 tuples in Z6? To answer that question, can you pick a pair of linearly independent vectors in here? Yeah. Let's see. Yeah, I guess we should probably check the determinant, right, of different choices, like how do these work out? Those determinants should tell me about whether or not those pairs of vectors are linearly independent or not with respect to Z6. So my feeling, my gut, and I don't have a proof of this, but my suspicion is if we get the determinant to 0 divisor, that means that they don't give you a free module basis. Is that true? What does it mean to have a free module basis for Z6-2? That means we should be able to take anything in Z6-2, which would be like x comma y, right? And write it as like x1 v1 plus x2 v2, right? Which is to say that we can take the concatenation of v1 and v2 and multiply it by the vector x1, x2, right? And get back to that. So when can you actually solve this equation for x1 and x2? Because solving this equation for x1 and x2 for arbitrary xy is tantamount to this being a free basis over z mod 6. So when is that? You need that this is invertible, right? If that's invertible, then you got it, v1, v2 concatenated inverted times xy, well, that's equal to your x1, x2. The existence of those x1 and x2 means that it's actually a free. I think that's enough. So it seems to me, and I know that the matrix over Z6 rather is invertible if and only if it's determined it's not a zero divisor. So our choices, there are many choices, right? So this is fine, and this is fine, if I understand correctly. In the sense that we could use basis what? What are our basis choices? Oh. Yeah. I guess -3, but we both agree. So count that out. So you had two choices. So our choice is basis beta 1. We can use 3, 2, 1, 5. Or we can use basis 2, which has got your 1, 2, and your 3, 1. And if we calculate beta 1 inverse A beta 1 for the usual linear algebra reasons, what will we get? And if we calculate this, what will we get? Where is that 3, 2 coming from? Let me write it under these. 3, 2 was from 0, right? 1, 5 was coming from the 5. You know, these are my eigenvalue here. 1, 2 was coming from the 2 eigenspace. 3, 1 was the basis for the 3 eigenspace. So the beta 1 will similarity transform it to 0, 0, 0, 5. This similarity transformation, on the other hand, will transform it to 2, 0, 0, 3. Kind of cool, right? So what I want is I want to find a similar example for like 2 by 2 hyperbolic matrix, all right? I want to find two different bases that will give me two different similarity transformations. And I want to look at the solution sets that these different choices generate and understand what is the connection between the solutions in these different choices. Because I know that whatever basis you pick, if theorem 17.7 supports it, for our example, there exist 2 by 2 hyperbolic matrices which are not diagonalizable. But if you pick one that is, right, if the roots are generous enough, right, we should look for, pretty clearly to make the example interesting, we need to look for one that has roots which are what? We want a 4-root matrix, right? If we get a 2-root matrix, that's not interesting, I don't think. As interesting. We're looking for a 4-root, one of the 4-root cases, right? For the hyperbolic 2 by 2. Oh, so there's your project for the break. No. So I gave this problem to Kang many moons ago. Kang proceeded to ignore my question and invent a general theory of to try to generalize something anyway. So, and I respect that, but still, the problem remains. We need to find an example. I mean, I paid Kang $0 for doing it, so I can't really fault him for not focusing on my boring question and instead pursuing more interesting ones. Kang is being polite and saying it's not a boring question. Will our pathological matrix work? The one that that one will not work, so we need something else. Let's do something like 1, A, B. Oh. So let's see here. Let's work.
Every matrix like found it always has.
Can we start with, let me start with a question. Let me start with what we want. We want to find the characteristic polynomial having 4 roots, right?
That's what I do, and they all
Well, diagonalizing is fine, but diagonalizing differently is what we're interested in. It's not that I'm trying to find one that won't diagonalize. I'm trying to find one that diagonalizes in more than one way. Oh, that is a separate and also interesting question. What hyperbolic 2 by 2 matrices are not diagonalizable? Oh, it still have 4 roots. Yeah, you notice, I mean, if you look at this book, it's nice. But that theorem, 17.7, I just quoted for you, that's kind of the end of the road in that book. There's no like, oh, here's the next chapter on the Jordan form over a ring. No, that is not there. What he does is that he's like, oh, if the ring's a principal ideal domain, everything's hunky-dory. And then he says the usual stuff, you know? It's like, yes, I know. But what, if anything, can you say past just, I mean, are there other theorems analogous to 17.7 that take the place of like Jordan form? That is generically the question that King was investigating, I think. Kind of, yeah. Okay, but we have a more specific question. So we could work backwards from the isomorphism. It occurs to me, right? So we have R cross R is isomorphic to H, right? And so if I want to have four characteristic values, how about if I look at the, you know, like x squared minus 4, y squared minus 3 equal to 0? Well, that has solutions. What's it got? It's got solutions plus or minus 2 comma 0. And, oh, sorry, plus or minus 2 plus or minus 3. The pluses and minuses are not connected. The 4 solutions are 2, 3, minus 2, minus 3, minus 2, 3, and 2, minus 3. This polynomial in the direct product of RR, this guy, is a, yeah. I don't want square roots. I guess I could be lazy and just try to look for an example in the direct product algebra, right? Why not? Is it too boring? So the direct product algebra, how can I get that as my characteristic? Characteristic of A, and so the variable here is xy, yeah? So we're looking at the determinant of x comma y times 1, 0, 0, 1 minus my A, which it would have things like A1, I don't know what's a good notation here, guys. I'm going to run out of letters. A1 comma B1, A2 comma B2, A3 comma B3, A4 comma B4. That would be this is my candidate for A, which is an element of the direct product algebra, the 2 by 2 matrix, 2 by 2 matrix in the direct product algebra of R with R. The reason I'm doing this is we've already tried, I mean, I've personally already tried with Kang in the past to see it in the hyperbolics, and we've had trouble. there's some kind of stumbling block there. Maybe this will help us see past that. So we want that to be, I don't want that just to be 0. I want that to be this up here, right? How does this work out? I mean, this is the determinant of, multiplying that in puts xy here, and it puts xy there, right? Is there something I'm doing wrong? Oh, okay. Okay, so then I take that difference, I get what? I get x minus a1, comma, y minus b1, minus a2, minus b2, minus a3, minus b3, x minus a4, y minus b4. Determinant, take the determinant, what's that give us? I'll do it down here. It gives us, again, something in the direct product algebra. In particular, it gives us x minus a1 times x minus a4, right? Comma, y minus b1 times y minus b4. Subtract from that these guys, right? So minus a2, a3, comma, b2, b3. And I do have a net minus there, right? Is that right? Yeah. Huh. All right. Now, so this is we just built a machine with 4 moving parts. Can we get rid of any of them? Do we just need to keep maybe 1 or 2 moving parts? Oh, there's 8 moving parts. Maybe we can get away with discarding some of them. I don't know. I mean, this gives me x squared, right? a1 plus a4x plus a1, a4, y squared minus b1 plus b4, y plus b1, b4, minus that thing. So can you guys see it yet? What to do? To get, my goal is to make this, right? I want it to match that. Well, obviously I need a1 plus a4 to be 0, right? I need, so these are not up for grabs. I need b1 plus b4 to be equal to 0. I need my a1 plus a4 to be 0, right? It would be nice, and I also need a1, a4, right? Minus a2, a3, is it? I need that to work out to what? I need that to work out to minus 4 if possible. And also I need my b1, b4, minus b2, b3 to work out to minus 9. Can we solve these? Mathematica. Ah, so weak. Killing me with the weakness. So how about this? We put b1 equal to minus, so that's a minus b1 squared, minus b2, b3 equals to minus 9. So apparently b2, b3